Okay, guys, welcome to the Waves unit. So this unit is a little different. We're going to take parts of 3 different chapters. So you will at times be reading and seeing chapters 20, chapters 21, and 22 a few different places. With the amount of time we have left this year, I'm kind of just combining the 3 chapters, which are on waves, wave energy, sound waves, and light waves, all into one little kind of chapter on waves, so wave energy. So this is the waves unit. A wave is any disturbance that transmits energy through matter or empty space. So a disturbance is a key word here because it is sort of a change, right? Either a change in energy or a vibration or some kind of alteration of the normal. Okay, energy is actually carried by a wave. Okay, so waves have energy. Waves are a form of energy. All right, they can impact things around them, but as you can see in this picture there, they don't carry material with them. So they go through a material or through a medium, but they don't carry other matter that's around them with them, as you'll see in the next slide even clearer. Okay, so here we've got a wave, a water wave, right? And the wave's motion is going from left to right. So the wave is moving from left to right, but is the leaf moving from left to right? No, it's not. The leaf is only moving up and down, right? So you can see here it's lower, and then the second one down here, you can see it's a little higher up. So work is being done on that leaf, but it's not moving this direction, okay? Only the wave is. So as a wave travels, it can go a certain direction, but it won't carry materials with it. All right, so waves do work on everything in their path, okay? However, as we saw before, the wave made the leaf go up and down. It also does work on anything else floating on the earth, on the water surface. So even though it's not moving with the wave, you can still tell the energy is being transferred there, right? Because anytime we're doing work on something, we are transferring energy. So if you think back to that picture you just saw, the wave is moving the leaf. It's doing work on it. Therefore, it's transferring energy. All right, so waves move through something called a medium. All right, a medium is a substance through which the waves can travel. So think about air as a medium, water as a medium, rock as a medium. Some waves can go right through mediums, but some can't. Some get stopped by them, right? So examples of waves are sound waves, water waves, and seismic waves, like found in earthquakes. They all need a medium to travel. So this list of waves here needs a medium to travel through them, right? And I put the picture of Alien there. If you guys ever seen the classic like 80s or 70s movie Alien, you can't see it's really small, but it says right there. It says, in space, no one can hear you scream. Well, that's accurate, right? And why can't they hear you scream? Because there's no air. Very good, class. Because there's no air, there's no medium for the sound wave to travel through, okay? So you can shout all you want out in space, but no one can hear you, unless, of course, you're on a spaceship with aliens. Then other people can hear you, but if other people are out in space, they can't hear you because no sound wave is made. So a seismic wave would do no damage, right, if it wasn't in the earth, right? The seismic wave travels through the earth, and for earthquakes, the medium is the actual rock and the soil of the earth. So you got to know what a medium is, okay, in this chapter, and that sound waves and water waves and seismic waves travel through one. Okay, so some waves, however, don't need a medium to transfer or to travel. So light waves, microwaves, including radio waves and X-rays, those are waves that can transfer. They can go from one place to another without going through a medium. So they don't need air, they don't need water, they don't need anything to travel through. So that's why the sun's rays can reach the earth, right? So those are light waves that are traveling through space, right, where there's no air, no nothing, and they can travel to earth because they don't need a medium. So all those waves that are listed up here, all these guys up here, these are all electromagnetic waves, all right, and which can go through matter. We're going to spend a whole section on electromagnetic waves later. So there's two main groups of waves. Transverse waves are waves in which the particle vibrates perpendicular to the direction that the wave is traveling, right? So if the wave is going this direction, that means it travels perpendicular, like this, okay? Right? So it's like the opposite direction that the wave's actually traveling, okay? Transverse waves are made up of crests and troughs. So the crest is this higher part here, and the trough is this lower part. So like think high, low, it goes back and forth. So water waves or a wave on a rope, if you kind of hold two ends of a rope and kind of, one guy's here and the other guy is here, right? And if one person raises his hand, you can kind of make a wave with that rope, right? That is a transverse wave, and electromagnetic waves are also transverse waves, all right? Hey guys, so the other type of wave is called a longitudinal wave. These are waves in which the particles vibrate back and forth along the path that the wave moves. So these waves are made up of two things called compressions and rarefactions. So if you think about your slinky or a spring, when you pull one end of the slinky or the spring, it compresses and then goes forward. That is a longitudinal wave. So if I'm drawing this again, the wave's going to go that direction. In this case, we're having an area of compression where the waves are close together, and then kind of a little bit less. Then again, another compression, and a little bit less. So that would be the compression, and that would be the rarefaction, where it kind of relaxes a little bit. So in this case, they're kind of moving in the direction of the wave. They're not necessarily moving perpendicular like the other waves. All right, so here's a good comparison of the two. So you can see here in the rarefaction are kind of where there's this sort of release almost of the wave, and then it compresses again, then it releases and compresses and releases and compresses, and that goes along in the direction that the wave travels, okay? Now the transverse wave, you can see that it goes up and down and up and down and up and down, these troughs and crests. Sound waves are longitudinal waves. So sound waves travel by compressions and rarefactions. So if you see this drum here being hit, when you hit the drum, there's a compression initially right here, then it kind of releases to this large rarefaction here. And in this case here, when you're hitting the drum over and over again, you can see a rarefaction, a compression, a rarefaction, a compression, again and again, okay? So sound waves involve this compression of air when the sound is made, okay? So there can be combinations of waves too. A transverse wave and a longitudinal wave can combine to form a surface wave. Surface waves look like transverse waves, but the particles of the medium move in circles rather than up and down. All right, so you can see the bottle as it moves in this direction here, from here to here. It's moving both transverse up and down, and also compressing back and forth to make that circle. It's a little confusing. Mainly, though, we're going to look at those other two types of waves. We're not going to see these surface waves too much. So now we're going to talk about properties of waves. So these are sort of how we organize waves and classify waves. All right, so, because there's all kinds of different sizes and types of waves. So here are the two main ways we do it. So amplitude of a wave is the maximum distance the particles of a medium vibrate from their rest position. So if this rest position is here in this kind of the center, it's basically how far it goes from the center, basically how large these crests and troughs are, okay? So more amplitude will have a larger crest and a larger trough, right? It carries more energy than small amplitude does, all right? So if I could kind of erase this really quick, I'll show you, if you're thinking about like a wave, like a spectrum of a bunch of different waves, like we're going to look at the electromagnetic spectrum later. Some types of electromagnetic energy have really large waves like that, and some have smaller. So I'm going to show you some smaller ones like that. They're kind of closer and closer together like that. All right, so this side here would have more energy, right, than the small amplitude does, so the higher it goes, okay? So again, amplitude is just how far it goes from that rest position. Wavelength is the distance between any point on a wave to an identical point on the next wave. So it's the distance between the two waves. So distance between here and the distance between here. So that distance, that is called the wavelength here. Okay? A wave with a shorter wavelength carries more energy than than a wave with a longer wavelength, right? So if there's a lot of distance between here, so the kind of a large wavelength here versus one that's like this. So this one here would have more energy than the first one I drew, okay? Because that distance is shorter wavelength. It's almost like you're like cramming more waves in that smaller space. Does that make sense? So just know that the larger wavelength means less energy. So frequency is the other main way we organize waves. So we've talked about wavelength, amplitude, and now this is frequency. This is a number of waves produced in a given amount of time. So frequency is usually expressed in something called hertz. 1 hertz equals 1 wave per second, right? So sort of the more waves you can produce, the higher the frequency. Okay, so if amplitudes are equal, high frequency waves carry more energy than low frequency waves. That just sort of makes sense, right? So if we're talking about amplitudes that are the same size, right? So here's our rest line here, right? Let's say these are two amplitudes, they're the exact same size, these two here. Waves that have a higher frequency, right, where there's more of them in a given amount of space versus less, this one here is going to have more energy than that, right? Because there are more waves in a given amount of time. All right, so here's sort of like a little summary of all our different our properties of waves here. You've got the wavelength, right? So the distance between each wave here. It looks a little bit different on a longitudinal wave and a transverse wave. Basically, it's the distance between the compression and the rarefaction, right? So if you have a compression here, and then your next compression's here, there's your wavelength, right? And as far as the transverse wave goes, you look at the top of the two crests, right? So, or the bottom of each trough, either one. So the distance between the two crests gives you your wavelength, all right? And you can see the frequency here, right? You can see how many waves pass this swimmer in 10 seconds. Could tell you the frequency of those water waves. Okay, so this is a pretty quick summary of the first lecture of this little unit. If you think you want to go back over anything, make sure you look at the first 2 sections of chapter 20. If you want to just look those over in your textbook, not a bad idea. We may be doing some textbook work in class, followed by a short quiz, so be ready for the quiz. Thanks and have a good night.